Hello everyone, this is Joy Datta, and today I am going to present our research paper entitled JUHDM, that is IoT-based honk detection and novel driver profiling for smart city. And my co-authors are Devajit Chakraborty, Sharvani Roy, and Deepak Uthal. It is worth mentioning that nowadays noise pollution in a city is a very big problem. World Health Organization recommends a general daytime outdoor noise level of under 55 decibel to prevent health impacts. So what kind of health impacts we can think of? So health impacts include hearing loss, sleep disturbances, cardiovascular issues, also mental health. So here, in terms of overall cities noise pollution, roadside noise played a crucial role in cities' overall noise pollution. To solve cities noise pollution, there are different approaches. Like air pollution monitoring, we could go for static noise pollution monitoring stations as well. But these kind of solutions are actually not feasible. Why? Because it will not give us the proper information of any particular place's noise pollution. Because as we know, like noise pollution, in terms of noise pollution, when we are getting noise value of any particular place, as the space between 2 points increases, the noise value decreases rapidly. So the same concept of air pollution will not be valid for noise pollution. So here the most effective approach is participatory sensing based approaches. So within these participatory sensing based approaches, the type 1 participatory sensing based approach is noise pollution monitoring through capturing ambient noises, including honking. So for this kind of solution approaches, we generally go for smartphone based solution where we capture all kind of noises, including our like surrounding noises, like when we are talking, this kind of noises as well as honking, everything is actually coming together. So this is the first type. And the second type is honk detection as a part of a bigger system where it is actually integrated with different IoT-based devices. The problem with the type 1 is when you are capturing all kind of noises, so basically you are capturing conversation as well. And there the issue of privacy comes into the picture. So the best solution in this kind of scenarios will be type 2, where IoT based solution we are looking for. So that kind of solution will be the most appropriate one. So here in this particular solution, in this particular paper, we focus on the IoT based solution, that is the type 2 solution. So what is the problem summary? So our problem summary, we can summarize it as we want to capture honking of the car accurately to control cities' roadside noise pollution and create dynamic driving style based driver's profile. This means we want to capture each and every honk that a car while moving on the road is actually giving to the society. All those noises that is coming from the honk of the car, along with that, the driving pattern or the how the driver is behaving on the road, we want to capture these two parts at the same time. So our main contributions could be summarized as follows. Design and development of IoT-based intrusive and non-intrusive solutions to monitor vehicle honking. So what is intrusive and what is non-intrusive? I'll discuss it very soon. The second point, real-time performance evaluation on the road for both solutions, means intrusive and non-intrusive one, to check their effectiveness by building and deploying their prototype. Okay, so here prototype for the first one is PNP HDM and the prototype for the second one is OBD HDM. I'll discuss these two very shortly. And the third one, provide a novel driver scoring mechanism that is based on the driver's driving style, including honking information. The architecture that we are following here comprises of IoT layer, edge layer, and cloud layer. In the IoT layer, we have D and R sense, that is drive and road sense. It's an IoT-based application. Another one is smartphone-based application, noise sense, and the third one is JUHDM, that is Judicious Urban Honk Detection Module. So here, in this particular scenario, we're actually merging these three applications together. So in the IoT layer, we are collecting all the information. So drive and road sense. Let us understand the first part. First part is drive and road sense. So drive and road sense is actually capturing our driver's driving pattern. So how our driver is driving, whether he is doing rash driving or not, how he is accelerating, whether he is accelerating very fast or he is braking too frequently. So this kind of information we are getting from the DNR sense. Whereas with the help of noise sense application, we are getting the ambient noise information. That means how much noise is there present in the surroundings, say like 70 decibel, 80 decibel, something like this. And now, along with these two, when you are clubbing JUHDM, that is Judicious Urban Honking Detection Module. So this is a particular module that we are using. So what we are getting? So with this particular module, we are precisely getting the information of the honking of a particular car. So along with the honking pattern, we are getting the driver's pattern, how a driver is behaving in the road, whether he is going smoothly, whether he is doing the rash driving, whether he is going like on a bad road. So road condition also we can detect, as well as what kind of scenarios we are facing, like what kind of ambient noise we are facing. So all those informations were clubbing together. And when we're capturing all this information in the smartphone, so smartphone is actually working as an edge device, and using this edge device we are doing some pre-processing in the local node, in the local smartphone, and then we are forwarding the data to the cloud for further processing. Okay, so this is how IoT layer, edge layer, and cloud layer come into the picture. So here our primary focus will be this particular section, that is D&R-Sense, JUHDM, and noise sense. Now, let us discuss the solution that I was discussing about, that is PNP HDM, that is plug and play based HDM. This is a non-intrusive solution. Why I am saying this is a non-intrusive based solution? Because for this kind of solution, we need not to cut any kind of wires in the system, that means in the car. We just plug the system in the car. That means there is, when we are designing this particular system to give power to this Arduino, we just need a USB cable. And if we plug the USB cable in the car, so basically this device will start working. So that's why it's a non-intrusive base. We need not to cut any wires. So that's why it's a plug and play based HDM. Here for design of this particular solution, we have used FSR 406 sensor. So here the strategy of this particular solution was like when we give pressure to any portion of this particular sensor, so the resistance of this particular sensor will change, and when the resistance changes, so current flow within this particular sensor also changes. So using this principle, okay, so we have actually designed this particular solution. So whenever we are putting this particular sensor just behind the honking module, so whenever we are pressing the honking switch, so basically this particular sensor is giving us the value of here in Arduino, in the Android, the Arduino pin A0 and A1, that we have pressed the button, and as soon as we are getting the information, so it is counting honking as 1. Okay. Similarly, the another solution is OBD HDM, that is intrusive one. Here the sensor that we are using is ACS712. It is a Hall effect based sensor. So here this sensor is more accurate, because whenever you are pressing the honking module in your car, so what you are doing basically in the circuit, current flows, and whenever current flows, this ACS712 module detects the same. So here you can see it's connected with the battery, whether it's internal horn or external horn, this ACS is actually connected with the both. So if there is any flow in the current in that particular circuitry, so it will actually detect that one, and it will give the same information in the Arduino, and we can detect the same information in our smartphone, because here we are using a AC05, that's the Bluetooth module that is sending the data time to time to our smartphone. Okay. And in real life implementation, so the first one, there is a PNP HDM we have implemented. Here you can see this is a PNP HDM module we put in the car. This is and this is the another model, the OBD HDM, that is another solution that we build and we put in the external horn of the car. Okay, so there are two different cars are there. This is Maruti Ertiga ZXi Plus model, and this is a Maruti model, but the model is different. It's a Maruti Desire. So in two different cars, we actually use these two particular modules, and we have taken some real world data. And based on that, we discussed the result section. But before going to the result section, this is the application that we are actually working on. So here you can see from the D&R-Sense. So we are getting this information, that is from the accelerometer. We're getting the XYZ information. This from the change of these XYZ values, we can get how fast we are accelerating, how we are doing the braking, whether potholes break, whether we can check all those stuff or not. Okay. Along with that, the noise sense module is actually giving this noise value. Whenever there is a honk is detected, what kind of noise value we are getting, so that value is coming here. Along with that, this is the portion of this particular section is actually reflecting that how many honks we have detected in the last 5 seconds. So here the count is 3 and the duration is 2600 millisecond. Similarly, it could be possible in the last 5 seconds there is no honking. It could be possible. Okay, and along with all this, we're also capturing the weather information to check further in future that whether there is any effect of the weather with the honking or not. Along with that, we're also capturing the land use data, that whether that in which area we are, whether it's a residential area or a industrial area. So what kind of impact it could have on the data. So to capture all those information, we are actually putting all this information together in the database. Now let's discuss how our designed JUHDM module works. As I was mentioning, that for this design, we have made the threshold to be 5 seconds. That means after every 5 seconds, we are sending data from the Arduino device to the smartphone. Okay, so here another thing we have assumed that the sensitivity to be 100 milliseconds. That means within two consecutive honking, there should be more than 100 millisecond gap. So this is the another thing. So this means actually if we are counting within last 5 seconds there were two time honking were discovered, so that means between these two honks at least 100 millisecond delay was there. Okay, that means we can see that between two honks there was a gap of 100 millisecond. Okay, and also when we're counting in this way, the total number of honks that is counted in the last 5 seconds, that is actually coming back to the app which is getting stored in the database of the smartphone. Okay, so here as we have mentioned that 300 is the threshold that we have discussed. Okay, 300 is the threshold that we have discussed. So whenever the driver is pressing the honking button, so basically the current flow and the time delay, all these things are coming into the picture. And as you see, for this particular line, cycle count is 50, less than 50. So basically maximum 50 times it can go round and round. And here if it counts or not counts, so basically here for each and every iteration it will take approximately 100 milliseconds. So 100 milliseconds into 50, so basically 5000 milliseconds. So 5000 milliseconds is equivalent to 5 seconds. Okay, so that's how the JUHDM is defined. Now let's check the performance of PNP, that is plug and play based HDM, and OBD based HDM. So keep in mind, just to remind you, PNP, this plug and play based HDM, is a non-intrusive solution, and OBD HDM is the intrusive solution. So since plug and play is non-intrusive, that means whenever we want to detect honking, we need to give pressure on the honking module that is based on FSR. So FSR means we need to press on that particular sensor to get the horn detected. So it is possible in real life when you are driving, so sometimes you will put pressure to some other place in the honking area, but still since the area in the car where the honking will happen, it's generally a circular way, so sometimes you might miss. So in our cases also we get the similar kind of result. So sometimes though the honk button was pressed, but we didn't detect the honking with the FSR sensor. So that's why, so when we go with side by side both the approaches, that is the PNP approach and the OBD approach, the PNP approach sometimes misses some honk counts. So over the overall these 19 trips, you can see in most of the cases it misses one or two, and that's why the average honk count with the non-intrusive one, that is in the blue color, is actually lesser than the average honk count of the intrusive one. Similarly, in terms of total time that is detected honking, so the time also, since it can miss one or two times, so basically that time duration also for the 1-2 time we miss that one as well. So that's why the average honk duration also a little bit is actually differing a little bit here in this particular case as well. But in terms of accuracy, when we checked with the ground truth, we found that the intrusive one is giving actually 100% accuracy, whereas non-intrusive one we are getting 90 to 95% accuracy. So both the solutions are quite good. And for your information, whatever the solution that is present in today's world, maximum we can get up to 90 to 92% accuracy. So both the solutions of ours are actually better than whatever the solutions are there in the market. Our next motto is to get a novel driver profile. So this is the first time we were trying to give something to the research world that no one has ever tried. So here what we were doing, we were trying to get all the information from the JUHDM, that is our design module, as well as the information that we were getting from the D and R sense, this is drive and road sense module. We are clubbing all these informations together such that we can give a realistic and real world based driving score that could be utilized by the government on the city authority or like the insurance company like this. So here what we did, we start like every day a person will be getting a score of say 100 at the starting of the day, and at the end of the day after whole day's drive the score will be either getting some reduced or will be at the same, something like this. The concept is like in different time segment of the day, like rush hour, daytime, nighttime, so different kind of points the person will be accumulating, as well as not only this kind of scoring mechanism. When we think about the long run, so dynamic bonus and penalty, these two things also we have incorporated in the algorithm design. Like a bonus is given to a particular person if the person is driving penalty free for the last 5 minutes. Also decrease the point of that particular driver more if he's driving he's honking more than 5 times in the last 10 minutes. In this way, in real world basis we are adjusting the score, and in this way excellent score means represents in our case like 80 plus, good score represents 60 plus, fair score represents 40 plus, and poor score represents less than 40 actually. And when we tested the same with different drivers on the road, so we get the similar kind of results. So here in figure A, actually you can see a good driver over the 1, 2, 3, 4, 5, 6, 7 over the trial period of 7 days. A good driver is actually generally getting good score. Okay, overall getting good score when he's driving around the city. Okay, and as expected, the bad driver is actually getting lower score in general. Okay, so in similar way, so in figure B, what you can see that overall driving pattern, like a good driver is generally go for short honk and they never go for the long honk because it disturbs the people most. Also in terms of sudden acceleration and sudden brake, so good drivers are actually using this kind of scenarios very less compared to other drivers. So in conclusion, we can say we have introduced a judicious R1 honking detection module. It's a very novel approach where we have designed and developed and tested two different kinds of modules of the JUHDM. One is the PNP HDM, that is the non-intrusive one, and the OBD HDM, which is the intrusive one. Out of these two, we find that the OBD HDM has a higher potential because it is very accurate in terms of measuring honking. Also, we proposed a driver scoring mechanism. It's a novel mechanism which actually uses real-world data of the driver to give a real-time score, which could be used in future by the smart city authority to give proper score to the driver, which is better than any other score that is available in the literatures. Thank you for your patience. Please feel free to contact me if you have any questions.